So there's kind of four area of access. So the first one is the aerodynamic part, so understanding the chemistry of what's going on in the atmosphere while these things are re-entering, these vehicles are re-entering. So that's number one. There's also the computational aspect, trying to make everything work, trying to model this in a large and efficient way. Then there is also a part on uncertainty quantification. And there's our part out of UK, which is the thermal protection system, the heat shields. So these four things have been studied a little bit on silos, I would say, closely with NASA all the time, but with individual researcher partnering up with one or two, but nothing of this scale, right? So the idea with Access right now is to bring everybody together and try to have a cohesive group. The project we have is a researcher that we've known each other very well over the last 10, 15 years. So it makes sense scientifically for sure, but it also makes sense on a personal level. So it's basically a lot of friends that are being able to work together towards these big projects. So there's Jack Maddox, which is a professor out of UK Paducah. He does experimental heat transfer, so we're going to have this base of students that are going to be located in Paducah and be part of Access. So there's also Dr. Savio Puvatinko, who does also atmospheric and heat shield modeling, but at a different scale than what I do. He does it at the very, very tiny, almost molecular scale. Then there's also Dr. Matt Beck from Materials Engineering, who will also look at property of the material that we're going to use. And there's the last member we have is Dr. Hailong Chan, who's in Mechanical Engineering, who does structural mechanics. So he's going to look at fracture, how these materials are behaving under high stress, and so on. A lot of the funds are going to get towards funding students. They'll be doing the main part of their research. They will interact with NASA. Typically, we send them at NASA every summer. Like this year, I think we probably have, just in mechanical engineering, probably have 10 students that are virtually going to NASA this year. So this is already going on, but through Access is going to be even on a bigger scale. So a student will be at the core of it. When you have uncertainty, you don't take any chance. So basically, if we're taking the example of heat shield, you say, well, according to my prediction, I need about an inch thick. And then you say, well, there's a lot of things that I don't know, so let's put 2 more inches on it. So it's completely over-designed. We don't care about sending a heat shield on Mars. We want to send a robot on Mars. And every mass, every kilogram that goes to the heat shield doesn't go to something useful, right? So the concept of useful payload here, the more heat shield we have, the less useful payload we have. So there's always this goal of trying to optimize the materials, optimize the way they're designed, understand the uncertainties, making sure that we know exactly what's going on. So these are complex systems. They're not basically a piece of material. They're a piece of material that's reacting to its environment. So it's meant to react. They're designed, they're two-phase materials. So one part of it is just vaporizing, and the energy of the vaporization is not going to thermal energy, so the temperature is not increasing. It's also cooling through this gas that's blowing within the heat shield, and they're meant not to be reused. Prime example of that is the one that was used on Apollo, for instance, the one that's used on the future Artemis mission. They're called ablative heat shield. They're not meant to be reused. They're one-time use, but they're very efficient. They have the ability to absorb the heat and take that heat and do something with that heat, which is not transfer it into temperature.